Let's start our next section, which is 3.6, and it's about derivatives of inverse functions. So we're going to start by recalling some facts. So recall, sometimes functions have an inverse function. So not all functions have inverses, but if a function is one-to-one, then it does have an inverse. A function needs to be one-to-one to have an inverse. So visually, you can think about inverses in the following way. You reflect your function, your one-to-one function, over the line, over y equals x, to get the inverse. So if you have a graph here and a function that is one-to-one, graphically what you do is you reflect over this line y equals x to get your inverse function. So let's suppose I have a function that has an inverse. Suppose f is a function that has an inverse. So we know some information about this function. So in particular, if f is continuous on its domain, then f inverse is continuous on its domain. So as long as your function you start with f is continuous, its inverse function will also be continuous. And the same thing applies for being differentiable. If f is differentiable on an open interval, or I'll just say on an interval containing C, and I know that when I plug C into the derivative, it's not 0, then f inverse is differentiable at f of C. So if you start off with a differentiable function and you know that the derivative is not 0 at C, then the inverse will also be differentiable, but at f of C now. So we want to know, how do we find the derivative of the inverse function? And there's this nice relationship, so call this derivative of inverse function. So assuming that f has an inverse function, and I'm going to call that inverse function g, then the derivative g prime of x will be 1 over f prime of g of x, provided that this is not 0. So now that we know how to find derivatives of inverse functions, we're going to use this in some problems coming up in the next video.